Hi everybody, it's Mrs. Dinkelman and we're in Unit 10 and we're starting to get into the sections where we're going to test whether a series converges or diverges. And what I mean by this is really we're going to have something with an infinite amount of terms and we're adding all those terms together, and if we could find that sum, would that sum be finite or infinite? So we have lots of tests to learn for this unit, and I'm just going to quick show you how, if you have the copy of the notes here, if you look at the appendix, there should be a notes catcher for these series tests. That way you can have this the series tests kind of all in one location. So they're all here, and I don't know that they're necessarily in the order that I have them in the book, but they're all there. So for this first section, we are going to be talking about geometric series and p-series. And a geometric series is probably something you've seen before. I always just say it's a times r to the n. I just wanted to put that subscript there because I want you to know that this a sub 1 here and this a could be different depending on where we start. So this is just kind of the generic form that a geometric series is going to look like. This is the type of series that we just keep multiplying by that same number over and over again. Rather than adding the same number, we multiply. And that's that r, or the ratio. We're going to be looking at the r to determine whether or not the series converges or diverges. So if that thing that we multiply by all over and over again is equal to or greater than 1, kind of barring the negative there, you'll see that we'll have a result that the geometric series diverges. If that r value, the ratio, is less than 1, then our series is going to converge. And again, what this means is when I add up all the terms in that series, that I'm going to get something finite, which sometimes seems a little odd that I could add an infinite amount of things but get a finite result. So one other thing with geometric series, and that is oftentimes they will ask us to find the sum. So what do they add up to? They don't ask that in all of these, but in the geometric they will. So we need to memorize this formula for the sum of an infinite geometric series. So that would be a over 1 minus r. A is the first term. So sometimes you can just tell a by the fact that it's sitting right there, but that's only if n is starting at 0 here. So if you just figure out what the first term is and then what you multiply by every time, that's the r in our summation. So let's go ahead and look at these 3 examples that have to do with the geometric series. So let's first, this one's not set up in sigma notation, and we could set it up in sigma notation if we wanted to, but we don't have to. Let's just write out what we think the terms are here. So first of all, I would say a is 5 because that's just the first term. R again is the ratio. The ratio is the thing that we multiply by every time. So from the first to the second term, it looks like we multiply by negative 2/3. Let's just verify that that works from the second to the third term. That's also a negative 2/3. So I think our ratio is negative 2/3. If we wanted to write this now, we could. Again, not necessary, but it's always a and then r to the n. So what we want to look for is what's the absolute value of our ratio. So the absolute value, well, yep, that is less than 1. So that fits into the convergence category. Now, if it converges in this assignment, I'm going to want you to go ahead and figure out what the sum is. So for our sum for example 1, it's going to be a over 1 minus r, which is 5 over, so 1 plus 2/3 would be 1 2/3, which would be 5/3. So this is 5 times 3/5 if I flip and multiply, so I get 3. So what I'm saying is, if we keep multiplying and getting all those terms and add everything together, that sum is heading toward 3. Okay, number 2 doesn't quite look like the right form yet, but what I notice about this one is the n's are only in the exponent, which tells me that this really is a geometric series. So I'm going to simplify this a little bit. So 2 to the 2n is really the same as 4 to the n. And then I'm going to rewrite this as 3 to the 1 and then 3 to the negative n. And let's just go one more step then. I have a 3 to the 1 and then I have a 4 to the n and a 3 to the n, and maybe even one more step, and maybe you could have skipped some in here, which is fine. And I have 3 and then 4/3 to the n. That's an n up there. So on this one, my a value is 3 and my r value is 4/3. Well, 4/3 is greater than or equal to 1, which means that this one diverges. It's an r, diverges. Okay, and then 3 is not exactly set up like a geometric series, but these also are. What we need to think about is really that this is like 0.08 plus 0.0008. Does that look right? 1, 2, 3, 4. Okay. And then 6 of them, I guess. 3, 4. 1, 2, 3, 4, 5, 6. And so on. So I'm going to just write this in terms of fractions. So that's 8/100ths, and this is 8 tens, hundreds, thousandths, 10,000ths, and so on. So I think my a value here is that 8/100. I know that could be simplified. My r value, well, let's see. All I had to do is multiply by 100 on the bottom. So that's my r value. Since my ratio, or the absolute value of that ratio, is less than 1, we have something that converges. And this, by the way, is just another way that we can figure out what the fraction is for this decimal. You might have had some other ways to do this in your algebra classes, perhaps. So I'm going to put the sum off to the side over here. So it's going to be a over 1 minus r, and some of you kind of already know this trick already. So that's going to be 8/100 over 99/100, which is really going to turn into 8/99. Okay. So geometric series, again, just to recap, has that specific form. The n's are only in the exponent, and I suppose on that example 3, I could have rewritten it in sigma notation just so you could see it. Okay, so we had a, and then we had r to the n. Let's try that again. R to the n. Okay. So again, the n's are just in the exponent, and that's one way to tell that something is a geometric series. The next one we're going to talk about, the p series, also has a very specific form. In this case, the n is going to be in the denominator, although we could have some algebraic manipulation we have to do, but there's a number up here in the p in the power. So that's why we call this a p series. What we are really looking for is for the p-value to be greater than 1. If that p-value is greater than 1, we will have something that converges. If it's less than or equal to 1, we will have something that diverges. There's a couple ways to show that works. There's a little explanation for the harmonic series, which is when p is equal to 1. That happens just kind of on the next page if you're interested in looking at that. So this one is a really straightforward test. It's just a matter of looking at what the power is on that n value that's in the denominator. So if I rewrite this example, so that's n to the 1 and n to the 1/2. So that ends up being 1/2 or 3/2. And so our p value is 3/2, which is greater than 1. So we have a p series here that converges. Okay, so that one, the p series, just looking at that power of the n in the denominator up there.